still manage to compute the square root of 2. Now here's what reductionism is. It's important for our discussion. And it's roughly the following. I've got a lower level theory, say quantum physics, quantum field theory or something. And I've got some higher level theory, for example, fluid motion in what's called the Navier-Stokes equation, which describes fluid flow. And the idea is, of a reduction, is that I can replace any statement in a higher level language by a whole bunch of statements in the lower level language, so that the higher level statement is a shorthand, literally a shorthand, for this bunch of statements in the lower level language. Everybody got the idea? So it's replacement but keeping the truth value. So the multiple platform argument now comes in and says, well, you can't do this replacement because you can't list all the possible physical systems on which you would manage to compute the square root of 2. So reductionism just doesn't work. Okay? Now another Nobel laureate, Robert Laughlin, has written a book called A Different Universe, the universe from the bottom down. And Laughlin says emergence is real also. So he talks about a couple things. If you try to measure the rigidity of an iron bar, you can't define it for a single iron atom. But you can, and the bigger the bar is, the more accurately you can measure it. So Laughlin wants to say, least controversially, that's emergent. Okay, it's not there in the underlying thing, it's there in the macroscopic big thing. Or a temperature, for example. You can't define it for a single atom, but you can define it for a pot of water. Then he wants to say something more controversial that I don't understand, and I want to go meet him at Stanford. He says, you know what? I think the fundamental laws of physics themselves are emergent from higher level laws in physics. They're not fundamental at all. Now, I actually don't know what Laughlin means yet. He means something. The guy's not stupid. Okay? So the message to take from this at this point is that really smart physicists are starting to doubt the adequacy of reductionism. This is already extremely contentious because we've all grown up with the idea from Newton that down there are the laws, okay, and everything else follows from the laws. And from that, it again follows that we are nothing but particles in motion. Whether it's a beetle, or Stuart Kauffman being found guilty of murder in court in Calgary or in Santa Fe, or a couple in love on the Seine. They are all, when everything is done, nothing but particles in motion. I'm going to try to show you next that that view is just radically wrong. But already the physicists are saying there's something wrong with it. So I want you to hold on to that. The view that's replacing it is called emergence. This is all still contentious, but it's making its way. Now what I want to try to tell you is, and I told you this was mostly a science talk, and it is. Now what I want to try to tell you is biology is emergent with respect to physics. Not that any physics law is broken, but that biology can't be reduced to physics. So let's start with the human heart, okay? And suppose we ask Darwin, Chuck, you may laugh, but my secretary awarded me the Chuck Darwin Chair of Theoretical Biology. And I always thought that Darwin would be pleased, you know, if he knew that I had the Chuck Darwin Chair of Theoretical Biology. We had it on the back of my chair for a while, and I was pretty proud of it. So suppose we said, Charles, what's the function of the heart? He would say, you know, it's to pump blood. And we'd say, but wait a minute, your heart makes heart sounds. It goes lub-dub. You know, it does. I got trained in medicine. It does. It goes lub-dub. He'd say, that's not the function of the heart. And then we'd say, well, why? And he'd say, well, look, the heart was selected in order to pump blood. That's what's the function of the heart. And then he'd go on to give a selective account, and he'd say something like, organisms that had hearts that could pump blood were more likely to survive than those that didn't, and therefore hearts exist in the universe, about which I'll get to in a moment, and that's the function of the heart. This is already interesting. In physics, the word function doesn't occur. It does for mathematical functions, but function in the biological sense isn't there. It's not a physics word. When a ball rolls down a bowl, it rolls down a bowl. It doesn't have a function. The next thing to notice about this is that a function of the heart is a subset of its causal properties. It is the pumping of the blood. It's not the making of heart sounds, right? So let's imagine that Weinberg could carry out his deduction upward, which he can't, because you can't even get to the Navier-Stokes equation for fluid, but leaving out some minor difficulties mathematically. Let's suppose, so I want to make it clear, I don't think there's anything remotely magical going on in your heart. There's no élan vital. It's just physics and chemistry and physiology. Okay. So let's suppose that Weinberg could get away with it, and he could deduce all the properties of Stuart Kauffman's heart, or your heart. Notice that he could produce all the properties of your heart, but he would have no way whatsoever of picking out the pumping of blood as of special relevance, right? It would just be another feature of your heart. He couldn't pick out the function of the heart. How could he do that? Well, first thing, he could become a biologist. He could know Darwin's idea. He could trace the evolution of the heart and say, see, it really was selected to pump blood. But then he's cheated and become a biologist. Let's not let him do that. The next thing that he could do, and I'm going to have to wait to tell you why he can't do this, but tell you, you may not agree with me, but I'll tell you. He could try to deduce from the Big Bang the evolution of the heart. Okay? It's going to turn out you can't do that. But that has to do with what I'll call Darwinian pre-adaptations. And I'll get to that in about 10 minutes. So just hold it. In other words, we can't do for the evolution of the biosphere what Newton taught us to do with billiard balls on a billiard table, where you know all the balls, you know the positions, the velocities, the momenta, the boundary conditions of the table, the initial conditions, and you compute the forward movement of all of the billiard balls. And we know you can do that. I'm going to show you can't do it for the evolution of the biosphere. That you can't is just stunning. But you can't, as far as I can see. So let's say you can't. Then you say, okay, Mr. Physicist, I'll tell you what. Since you can't do that, because Stu says you can't, he's going to convince us in 10 minutes. Why don't you simulate the evolution of the biosphere? Turns out you can't do that either. And here's why. You all know about quantum mechanics. I mean, Einstein is one of the villains in his paper on the photoelectric effect, for which he got the Nobel Prize. In quantum mechanics, quantum phenomena are real in the biosphere. So, for example, cosmic rays come in and zap you, and they may cause mutations that alter the proteins that you make, that therefore, or the genetic regulatory network, that alter the organism, which therefore may really affect the evolution of the biosphere. Or it doesn't have to be cosmic rays, it's just some other quantum phenomenon that alters what happens. Well, quantum phenomenon on the standard Copenhagen interpretation and Born rule are acausal and completely probabilistic. There's nothing causing it, and it's the only pure randomness in the universe. There are other interpretations of quantum mechanics that I don't want to get into.